Yes.
Okay, great. So Romero, I have a question about section 12.4. Let's see, where's my, let me share my pen. Okay. Let's see. Okay, let's see. My pen seems to be not following me. Oh, there we go. So draw. Okay, so section 12.4, number 19. This is about find all points at which the tangent plane to the graph of z equals to x squared minus 6x plus 2y squared minus 10y plus 2xy is, okay, horizontal. Okay, so think about if you have, okay, this is x, so y, z. Suppose you have a certain horizontal tangent plane. This is horizontal tangent plane. So for this horizontal tangent plane, its equation, right, has to be z equals to certain constant. Make sense?
Mm-hmm.
Okay. So it would be horizontal, right? Which means it's the equivalent at z minus z sub 0 equals to a constant to the right-hand side, which is 0, right? But in general, we understand that, let me see, where's my pen? So in general, we know for a tangent plane, it's z minus z sub 0 equals to the gradient partial x times x minus x 0 plus partial y minus y sub 0. Right, that's the equation. Tangent plane at x of 0, y 0, and z sub 0, right? So if we want to have the right-hand side being 0, this whole thing needs to be equal to 0, which that implies the gradient of x needs to be 0, and a gradient, the partial x should be 0, and then partial y should be 0, which means the gradient of function should be 0, okay, at that point. And we've said in terms of the gradient, it's kind of like similar to the slope of tangent line. And we know if the tangent line is horizontal, slope needs to be 0. Now tangent plane needs to be horizontal, therefore the gradient needs to be 0, right? Mm-hmm. Over here, partial x is pretty easy to see. This would just be 2x minus 6. So partial x needs to be 0. X would be 3. Partial y would be 4y minus 10. Oh, sorry, partial x, there's also this part, right? Plus 2y. Plus 2y. Partial y would be 4y minus 10, and then plus 2x equals 0. So we're just going to solve this equation, system of equation of these two equations, right? 2x minus 6 plus 2x, 2y equals 0, and 4y minus 10 plus 2x equals 0. And once you reach this step, I think Romero will be easy for you, right?
Mm-hmm.
Just solve the system equation for x and y's.
Yeah.
Okay, so the key here, when it comes to horizontal tangent plane, you understand the gradient, which is like analogy to the slope, needs to be 0. So partial x and partial y both set m equal to 0. Okay?
Mm-hmm.
All right, anything else? Any other questions, folks? If not, then we're just going to continue to talk about where we left last time, okay? And then we'll start a new section. Let me pause this share, and I'm going to, let me see. Resume share, stop share. I need to do a new sharing. So share this screen here. Okay, you guys see my slides in front of you, right?
Yes.
Okay, great. So very quickly, let's kind of review what we did last time. Okay, last time we were at maxima and a minima. Okay, very quickly, let's go over. We understand maxima and a minima is referring to the extreme values of the function. Okay, so there are two types of extreme values. One is called absolute extrema. One is called relative extrema. You know the difference between those two, right?
Mm-hmm.
Absolute extrema is just over the entire domain. Relative extrema is only over a small neighborhood, right? Small neighborhood, relatively high or relatively low. This graph here shows absolute max and absolute min, okay? And we said the existence of extrema is confirmed if the function is continuous and simply defined on a closed bounded region. So if there are such two conditions, you can be sure that the function must have a minimum and must have a maximum. Okay. And then we went ahead and talked about what is considered to be the critical points of function f. They're called the critical points because they are the locations where relative extrema may occur. Okay. The critical points, we said there are two types. One is called a stationary point, referring to gradient being 0. One is singular points, referring to the gradient doesn't exist. Okay. And these are pretty consistent to what we have learned in Calculus 1 as well. Okay, and then we went ahead and introduced a second partial test. This second partial test is used to determine exactly whether the critical point will give you a local min or local max. Kind of similar to the second derivative test in Calculus 1. Okay. So basically, you look at the second partial derivatives and check whether it will give you local min or local max. And here is the second partial test. This must be at stationary point, and you look at the d, which is a combination of all the second partial derivatives, right? It will give you some conclusion when d is positive. Then you know there's relative extrema, and you go ahead and check this, the sign of the second partial derivative with respect to x. If it's greater than 0, then you can refer to this graph, right? Second derivative being positive, it's local min. Second derivative being negative, it's local max, okay, which is relative min or relative max. Okay. If the d is actually less than 0, then the point would be a saddle point, okay, which means it doesn't give you local max or local min. Okay. If d happens to be 0, then the test doesn't give you any information, inconclusive. We did example 3 following the steps of second partial test. First of all, you look for critical points, especially stationary. Then we applied second partial test to determine whether it gives you relative max or relative min. Okay. And I think we went, yeah, so we stopped at this topic, absolute extrema, right?
Mm-hmm.
Okay. So absolute extrema, everybody has already understand it's over the entire domain that they're talking about, right? So it should be the entire domain. You should look at everything. Okay. So in general, absolute extrema can occur in two ways. It can be at some relative extrema. Relative extrema might happen to be absolute extrema. And second, absolute extrema can also occur at a boundary point. Okay. So in general, when you look at absolute extrema, we can just put this in short. Absolute extrema can occur at boundary points, right? It can be occurring at the relative extrema, which is referring to stationary point or singular point. And these two, we've looked at them last time, right? These two are for relative extrema, okay? Now, in addition to the relative extrema, which is in a small area, now for absolute extrema, you should also consider the boundary points, okay, boundary points. So we are just looking at one more type of points, which is the boundary points. However, sometimes the boundary points are very important because the absolute extrema may happen to occur on the boundary points, okay? Is that clear?
Mm-hmm.
Okay. So this is kind of like a summary. Absolute extrema may occur at stationary point, singular point. These two are both referring to gradient of function f. And then boundary points, which based on the definition, right? Definition. It will be given. So we're going to focus our time today, first of all, on example 4. This is actually a pretty long question. That's why, first of all, you guys take a look at this question. So they're asking you to find the global maxima and a global min, which is also absolute max or absolute min value of function f on the S, okay, on S, and indicate where those maximum or minimum would occur. The function is x squared minus 6x plus y squared minus 8y plus 7. This is the function. And the corresponding domain, okay, the domain is actually x squared plus y squared less than or equal to 1. So if I try to put this in a GeoGebra 3D calculator so you guys can visualize it, okay, this blue surface you see right down here, this is the function f of xy. Okay, is that clear, guys?
Mm-hmm. Yes.
And this corresponding domain, this is the domain, right?
Mm-hmm.
The domain S is actually referring to the points x, y, such that x squared plus y squared is less than or equal to 1. This one is actually just on xy plane. So this is x-axis, here's y-axis. If you look at the xy plane, this basically is referring to a circle, right? Is that a circle?
Mm-hmm.
It's inside and on a circle, right? So basically it's referring to those points. Can you see here on my graph?
Yes.
Okay. So on these graph, for this particular S, here is my S. Right, here's my S. And you can tell that if I simply try to project this S onto the graph, onto the surface, it's going to be these part of the surface here, right? So it's talking about not the entire, this blue surface, it's only the part of the surface that is simply projected over this circle. Is that clear?
Mm-hmm.
Okay, so you are looking at the maximum and a minimum of the function over this area, okay, over this small area, not this entire big surface. Okay, so you're looking for the max and a min of this f over this s. Okay. So we can tell that this surface, this specific domain S is closed, right? So this S, is that closed?
Yes.
Folks, right, this is closed and bounded, right? It is closed and bounded. Function f is obviously continuous because it's a polynomial function, right? Continuous. So function f being continuous and s being closed and bounded, therefore, according to the theorem, function f must have max and min over the specific area S. Okay. The extreme values must occur, okay, must exist over this S. The question is where and what are these extreme values? Okay.
Mm-hmm.
So let's just kind of like follow what we just discussed. We're looking at an absolute extrema. So let's consider the three types of points where the absolute extrema may occur. Okay, stationary point, singular point, as well as the boundary points. Okay, so I'm going to use this slide. Okay, so first of all, let's consider stationary point or singular point. Okay. Stationary point or singular point is both about gradient of f, right? So gradient of f, we have partial x. Here is pretty straightforward. That's just 2x minus 6. That's partial x. Partial y would be 2y minus 8. Is that good, folks?
Yes.
Okay. So the gradient both exists. Do we still have singular point possible? Remember, singular point is where the gradient doesn't exist. Okay. Over here, the gradient always exists, right? Gradient always exists. So there's no singular point. Okay, no singular point. There's no singular point. And we can only have stationary point. So let us set both partial x and partial y be 0 for stationary point. And obviously it's easy to solve, right? X would be 3 and y would be 4. So stationary point at 3, 4. Okay?
Mm-hmm.
So that's one of the options, right? We have stationary point at 3 and 4. We can check whether it will give us a local extrema. Okay, so let's do second partial test. Second partial test will be about D, which is fxx times fyy minus fxy squared, right? At this point, 3, 4. That's fine?
Yes.
fxx here, fxx would be 2. fyy, second derivative, second partial with respect to y, would be 2 again, right? fxy would be partial derivative with respect to y of fx. fxy would be, guys?
0.
0, correct. So 0 squared, which is 4, right? So D is indeed greater than 0. Oh, that will tell us at 3, 4, it will give us certain local extrema, right?
Mm-hmm.
At least D is greater than 0. So D is greater than 0. Next, we should investigate the sign of fxx. So fxx, according to what we just looked at, it is 2, which is greater than 0. Okay, so second derivative being positive, this critical point, the stationary point, will give you a local
minimum.
Yes. So local min at 3, 4, right?
Mm-hmm.
And we can further get local mean of value of f of 3, 4. Let's calculate this local minimum value. Okay. So the value will be f at 3, 4. Let's plug 3 and 4 into the function for the function value. So that's going to be 3 squared minus 6 times 3 plus 4 squared minus 8 times 4 plus 7. Okay. Quick computation. So we do 9 minus 18 plus 16 minus 32 plus 7. Okay, so that's minus 25 plus 7. Do you guys get negative 18? Folks, you guys have that as negative 18 as the local minimum amount?
Yes.
Okay, good. So we got one conclusion. At least there is a local min of negative 18, right, at 3, 4. Let's first box this conclusion. But we have said this is a local min. Whether this would be absolute min or not, that's still a question mark. Okay. How do we determine whether this local min is indeed absolute min or not? What do we need to consider?
Can you repeat the question?
Okay, so we have determined that the function has a local minimum value of negative 18 at 3, 4. But how do we make sure this is actually an absolute minimum or not? Is there some other values we should compare this negative 18 with?
You could probably use other values near 3, 4.
Yes, we need to compare that with other values. Correct, that is correct. What is the other value we should consider? Let's go back to our previous slide.
The boundary point?
Correct, there is also boundary point we haven't considered, right?
Mm-hmm.
So we already know there is a relative minimum, okay, but we haven't considered boundary points yet. Next, let's consider the boundary points, okay? And we can check the function value at the boundary points, compare that with negative 18. Good. All right, so next, so item 2, we'll just do second. Consider the boundary points. Okay. The boundary points are the boundary. Okay, so let me just plot the S again. So S is this closed set, right? Closed set is looks like a circle here. This is X, Y. Here's 1, negative 1, 1, 1, a negative 1. So this entire closed set is S. The boundary would be these, right? These would be the boundary. If you look at the boundary. So boundary is the points exactly on the circle. You guys agree?
Mm-hmm.
Okay. So boundary points would be those point X, Y, such that X squared plus Y squared happen to be 1, exactly equals to 1, right? On the boundary. So we should consider basically the values, okay, f of x, y, for those points x, y, such that x squared plus y squared happens to be equals 1. For these points, okay. Now, this question actually could be solved in next section when we introduce Lagrange multiplier. We have a systematic way to do this extreme value problems. But over here, we can still do it even without introducing that new section. Okay. I would like to remind you guys, where do you see this x squared plus y squared equals 1? Is there an identity that you can recall that fits some square plus some squares equals 1?
Sine and cosine.
Yeah, sine and cosine, right? So let's do a trig substitution. We can let x be cosine theta, y be sine theta, right? So x squared plus y squared has to be 1, right? They would fit this unit circle. Make sense?
Mm-hmm.
And then our function value, so f at cosine theta, sine theta, okay, the function value will just be x squared, so cosine theta squared, minus 6 times x plus y squared minus 8 times y and plus 7. So the function value at those boundary points turns out to be expressed in terms of these sine and cosine using trig substitution, right?
Mm-hmm.
Let's see, can we simplify this further? Now, remember, here's a cosine theta plus sine theta again, which is 1, and plus 7, that is 8. Here you have minus 6 cosine theta minus 8 sine theta. Right?
Mm-hmm.
Okay. We have successfully expressed the function value at those boundary points by using the variable theta. Okay. And next is we're looking for if there happens to be any maximum or minimum value, right, of this expression. With this expression, what's the max or min, right? How do we do that? How do we find out the max or min of this expression?
Take the derivative. No, wait.
Correct. Mm-hmm. Take the derivative with respect to theta, right? So let's take, this is actually a function of theta now, right?
Mm-hmm.
So let's take derivative with respect to theta. This goes back to calculus 1, single variable, right? Single variable theta. You are looking for extreme value. So take derivative with respect to theta. So we have 6 sine theta minus 8 cosine theta, so that'd be 0, right?
Mm-hmm.
Okay. So that gives you 3 sine theta if I divide by 2. 3 sine theta minus 4 cosine theta would be 0, right?
Mm-hmm.
Does that tell us that 3 sine theta is the same as 4 cosine theta?
Yes.
I move the 4 cosine theta over, okay? So that means sine theta divided by cosine theta, if I just move the things along, okay. What is that? Sine theta over cosine theta.
Tangent.
Yeah, tangent. So tangent theta should be sine over cosine. According to this identity, we should have 3 sine theta equals 4 cosine. So tangent theta should be 4 over 3, right? 4 thirds. Okay. However, this still doesn't tell us where exactly those x and y's are, right?
Mm-hmm.
Let's keep using our knowledge of tricks. I'm going to move on to the next slide. Would that be fine, folks? Because I'm running out of space here.
Yeah.
Okay. Oh, gosh. I thought there was another empty. Okay, let me see if I can add a slide. So insert any slide. Let's just duplicate. Okay. All right. Now let's go find here. Okay, so we have already known that tangent of theta equals, is it 4 thirds?
Yes.
Okay. And keep in mind, those points we're looking at is on the unit circle, right? Mm-hmm. So the point must have a tangent theta, which is 4 thirds. Fourth tangent is positive here in first and third quadrant. Tangent is negative and negative in second and fourth quadrant. So the theta must be in first quadrant or third quadrant. Is that clear?
Mm-hmm.
And 4/3 means y is 4, and y is longer than your x. So somewhere over here, right? 4/3. Okay. So it should be referring to this point and this point. Okay. So these 2 points. Okay. So these 2 points, the derivative happens to be equal 0. Okay. So this is xy. Here's another xy. Okay. Now I'm going to sketch a right triangle. Let's use the right triangle approach to find the xy. Tangent is, here's theta. Tangent is opposite divided by adjacent, so 4/3. Hypotenuse would be 5, right? 3, 4, 5. You guys with me?
Mm-hmm.
Okay. And we know that according to our trig substitution, x would be cosine theta and y would be sine theta, right?
Mm-hmm.
So let's refer to this graph over here. Okay. If you refer to this graph, x would be cosine theta, which would be 3/5. Y would be sine theta, which would be 4/5. Is that clear?
Yes.
Okay, and this is actually referring to this point, right? This point, because that's in quadrant 1. Okay, so point P1. Let's call this as P1. This is the first point that may give you minimum or maximum, okay, over the boundary points. So P1. So P1 is going to be 3/5 and 4/5. And according to our graph, there should be another point, which is in the 3rd quadrant here. P2. P2 should have the same tangent value, which is 4/3. Of course, when it's in 3rd quadrant, tangent will be positive as well. So you can tell the symmetry between these 2 points, P1 and the P2, right?
Mm-hmm.
They are symmetric with respect to the origin. So by looking at the coordinates of point P1, you can get the coordinate of point P2 very easily. Okay. We'll just need to negate both x and y because they are in quadrant 3. So -3/5, -4/5. Okay.
Mm-hmm.
So these 2 points may give you, right, max and min, because these points, the derivative equals to 0 for the function. Okay. All right, so let's go ahead and further investigate their function value. So function value at P1 and function value at P2. Let's check their function value, right? To see would these function value happen to be a very big amount or very small amount. Okay. So f of 3/5, let me write, this is the function, right? Function is x squared minus 6x plus y squared minus 8y plus 7. So let's plug in, and we already know that x squared plus y squared equals 1. Okay, this is 1. So that's 8 minus 6x minus 8y. It's 8 minus 6 times x, okay, x, 3/5 minus 8 times y, 4/5. Same for the second one, we should have 8 minus 6x minus 8y. That is 8 minus 6 times -3/5 minus 8 times -4/5. Okay, you guys calculate these 2 function values and let's make a conclusion later on. Where would the function have the absolute max and absolute min? Okay. Folks, have you got this?
Yes.
The function values? Okay, what is f of 3/4, 3/5, 4/5?
-2.
-2. What is the second amount, Romero?
18.
18. Okay. Great. So we've got these two function values, but what's our final conclusion then? Shall we consider all those extreme values we have got so far? So first of all, we have got this extreme value, right? Local min of f(3,4), which is -18. So there is a -18 function value at 3,4. And we have -2 at 3/5, 4/5. And we have 18 at -3/5, -4/5. Do we have a max here? Global max. Let me just write here. Do you see the maximum? The maximum function value. We've got -18, we've got -2, +18. Which one is the max?
-18.
Yeah, +18. Okay, let me just summarize here. So in summary, okay. So inside of S, right, we have a function f at 3,4, which gets you the amount of -18. Okay. On the boundary, we have f of 3/5, 4/5 getting you -2, f of -3/5, -4/5 getting you +18, right? Okay. I think this will be easier for you guys to see, right? So we can tell this is going to be the absolute max, right? 18 is going to be the absolute max. And -18 is going to be the absolute min, right? Absolute min. So let's put this in conclusion. Therefore, the function f of xy has an absolute max of 18 at the point -3/5, -4/5. Function f of xy has an absolute min, min of -18 at 3/4. So that's the end of this question. Make sense? This question is a little bit complicated because we have to investigate both inside of the domain, which means not considering the boundary, and on the boundary, right, on the boundary. For the point inside of the domain, you can just use the second partial test to find the local extrema. This is a local min. And it turns out this local min is also an absolute min, right? Originally, we said this is local min, but later we confirmed this is also an absolute min. And then we should consider the boundary points. The boundary points here is a little bit complicated. We see it's x squared plus y squared equals 1. So we can use the trig substitution, or you can say, let me introduce the polar coordinates. By using the trig substitution, you can find its extreme value at these 2 points, 3/5 and 4/5, -3/5 and -4/5, with these two with these two function values. Put all 3 together, we can find the absolute max and absolute min. Okay. So it's kind of interesting here. The absolute max here occurs on the boundary, right? Occurs on the boundary. The absolute min occurs inside of the set S. Any questions for this problem? This is a pretty long question. I want to make sure that you guys understand this before we move on.
Where exactly did the 3/4 come from?
3/4? Oh, the 3/4? Okay, let me see. Did I copy the wrong question here? Yeah, 3/4 is the local min. Remember, 3/4 is the stationary point.
Oh, good.
Right?
Yeah.
We first consider the stationary points to find the local extrema, and then we consider the boundary points. Okay. So the step 1 is about a stationary point, right? We found the stationary point here at 3/4. Using second partial test, we figure out this is a local min, which is -18. And then we consider the boundary points, right? Boundary points give us these 2 critical points whose function values are -2 and 18. Putting all 3 together, you can summarize and get a conclusion of the absolute max and the absolute min. Any questions, folks? Okay, it's easy to see that we spend lots of time in the second part, right, when we're considering the boundary points. The boundary points here, we're able to use trig substitution to find the max and min. It's pretty complicated, and actually this problem can be solved in the next section by using a systematic method called lagrange multiplier. So we're going to move on to the next section and see how we can solve the extreme value on this boundary by using an easy method. Okay? So we'll revisit this question again and check the alternative method to solve the second part of this question. Okay, before we move on, I'd like to check with you to see if any other questions you guys may have. Feel free to ask any problems any confusions you had over these several slides. No problem? Okay, so I'm going to save this over here. I'm going to keep the ink annotated and then open a new slide. Okay, a new slide here, which is section 12.9. Okay, the section 12.9 is the method of Lagrange multipliers. Okay, so we're going to introduce a new concept, which is called Lagrange multipliers. This method is used to solve constraint optimization problems. Okay, so we need to kind of introduce what is considered to be constraint optimization problems. And use the method of Lagrange multiplier. Sometimes you can also use this for 2 constraints. Okay, I'll give you 1 minute to take a look at this slide first of all. So in short, this method of Lagrange multiplier is used to solve optimization question. But this optimization problem comes with constraint. So it's called constrained optimization problem. Okay. We're going to first look at what is considered to be constrained optimization problem. Constrained optimization problem would have a general format. Okay, you're either maximize or minimize certain function, right? Maximizing or minimizing. Optimization. Okay. Subject to certain condition. Okay. So f of xy subject to some condition g of xy equals 0. Is that clear, guys?
Mm-hmm.
Okay. Now let's revisit the one that we just looked at, the section 12.8, right? 12.8, the last example. Remember on the boundary, we spent a lot of time on that part. So we're trying to maximize or minimize the f of xy, which is x squared, let me see, x squared minus 6x plus y squared minus 8y plus 1. That is the target function, right? Target function you are maximizing or minimizing. The points on the boundary, they are subject to the condition that they must be on the unit circle, x squared plus y squared equals 1. See that?
Mm-hmm.
So this is actually a constrained optimization problem itself. Okay, itself. So you are finding extreme values of this function subject to the condition x squared plus y squared has to be equals 1 for those boundary points. Is that clear?
Mm-hmm.
Okay, so this also fits the Lagrange multiplier method, its application problems. I'm going to look at, introduce this problem for you guys. To see how this technique works, consider the problem of finding the rectangle of maximum area. So you see, we're maximizing the area. That can be inscribed in the ellipse, x squared over 3 squared plus y squared over 4 squared equals 1. You see, this is an ellipse, right? Ellipse as given over here. And you have rectangles that can be inscribed inside of this ellipse. We want to find the rectangle with the maximized area. The points can be moved, right? The point xy can be moved. And you want to find the point that will give you the maximized area. Okay, so we're trying to maximize total area. Area of the rectangle, right?
Mm-hmm.
Let's suppose I have a point because the rectangle must have 4 vertices. So 1, 2, 3, 4. Let's suppose one vertex has to be in the quadrant 1, right? Suppose this is the point xy. So how do we express the total area? Area should be, yeah, length times width or base times height, right? Base times height. It's easy to see if this is x, what's the base? If this
2.
length is x, yeah, 2x, so it would be 2x. Similarly, for the height, if this is y,
2y.
Then on the y, right? Yeah, so it's a 2x times 2y, which is 4xy. So we're trying to maximize 4xy. This is the function, right? Subject to the condition that the condition is the point xy must be on this ellipse. Is that clear?
Mm-hmm.
Right? It can't go anywhere else. It has to be on this ellipse. So it should fit the equation of the ellipse, which means x squared over 9 plus y squared over 16 should equal to 1. So if we write it out, that's going to be the constraint optimization problem we are solving here. Make sense, folks?
Yeah.
Okay. So over here, objective function is 4xy. The constraint, as we have illustrated, is x squared over 3 squared plus y squared over 4 squared equals 1. Okay. These two elements are what you need for Lagrange multiplier method. So method of Lagrange multiplier. Okay, so now you must be very curious. How do we actually, what is exactly the method of Lagrange multiplier, and how do we use this Lagrange multiplier method to solve such constraint optimization problem? So we're going to introduce this famous method here. Okay. It has several steps. We just literally follow the steps. Okay. To find a maximum or minimum value of a function f of xy subject to the constraint g of xy equals 0, first of all, form a new function. Okay. The new function would include the original variable x and y. It will also include a new variable lambda. The lambda is the Lagrange multiplier here. Okay. So the function xy also with the inclusion of lambda, that's going to be the new function for Lagrange multiplier method. And how do we get this function? Pretty easy. It's going to be the objective function f of xy subtract this lambda, which is the Lagrange multiplier, times the constraint. Here's okay. So you just do the objective function minus the lambda times your constraint. And that's going to be the new function you need to construct for using this method of Lagrange multiplier. Step 1. Step 2. There are 3 variables now for function f you just constructed, x, y, and lambda. So let's take partial derivative of each and set them equal to 0. Kind of like finding the critical point, right? So set the 3 first partial derivative and set them all equal to 0. And once you set them equal to 0, you solve the system. Okay, solve the system. And you get the solution. Okay, so solution. If the solution is a, b, which is 4x and y, and lambda, then this solution would give you either a max or a minimal. Okay. So the method itself is pretty straightforward, right?
Mm-hmm.
You first of all form a new function, and then you take the first partial derivative with respect to all the variables you see, and set all the partial derivative equal to 0. Solve the system. That will give you the points where the max or min would occur. Okay, so let's go ahead and use this method to solve the question we just started with. Okay, this question here finds the maximum area of this rectangle when the point needs to be inscribed in this ellipse. Okay, so we are maximizing f of xy equals 4xy subject to x squared over 9 plus y squared over 16 equals 1. Also, because xy is in the first quadrant, so we let x be greater than 0, y be greater than 0. Okay. But you can tell that x and y could be other values, could be in the second quadrant, third quadrant, and fourth quadrant. Okay. But that's kind of like the general format we have here. Okay, so we already have f of xy, that's perfect. And what's going to be our constraint? G of xy. Did you notice that? Yeah, I'm sorry. You go ahead, Romero.
I was going to say the area.
The area? Oh, this is the objective function. Okay, this is objective. Constraint is about this, right? This is the constraint. Now, when we are using Lagrange multiplier, the constraint function needs to be g of xy equal to 0. So the right hand needs to be 0. Let's first change the look of this. Okay, so let's move the 1 to the left-hand side. So right-hand side will be 0. So I'm going to say x squared over 9 plus y squared over 16 minus 1 equals 0. That's equivalent to original constraint, right? So this would be my g of xy. F of xy, objective. G of xy is this constraint. Good? Okay, so we're going to use method of Lagrange multiplier here. First of all, let's introduce f of xy lambda, which is composed by objective function along with the constraint function. So the f of xy objective minus lambda, our multiplier, Lagrange multiplier, times the constraint g of xy. Okay. Let's copy our material. So we have 4xy for the objective minus lambda times constraint. Constraint is this part, so x squared over 9 plus y squared over 16 minus 1. Good so far? Okay, next is pretty straightforward. Let's take partial x, partial y, and then partial lambda. Partial x, okay, we could do 4y minus partial x will be lambda times 2x over 9, right? Partial x equals 0. Next, partial y. So partial y would be 4x minus lambda times partial y. So we did 2y over 16. That equals 0. The partial lambda. Partial lambda basically is just about this part, right? It's about the constraint. So the negative of x squared over 9 plus y squared over 16 minus 1 equals 0. This is basically rephrasing the constraint, right? Is that equivalent to the constraint that we had? Okay. So now we have equation 1, equation 2, and equation 3. So we just need to solve the system. Okay. Solve the system for x, y, and lambda. Okay, now a lot of times when you're solving system, you can use method of substitution, you can use method of elimination, right, for solving a system. If you look at this system, you can see that equation 1 and equation 2 has variable lambda. Equation 3 does not have lambda at all. Is that clear, guys? So if we can eliminate lambda from the equation 1 and 2, then we're down to 2 variables only instead of 3 variables. Is that clear? So my goal is, first of all, eliminate lambda by equation 1 and equation 2. And here's a trick way we can do it a lot of times here. Let me move the lambda to the right-hand side. So equation 1 is the same as 4y equals lambda times 2x over 9. Okay, equation 2 is 4x equals lambda times 2y over 16. When you look at these two equations, what's the quickest way you can get rid of the lambda? What kind of operation would help you to eliminate the lambda right away? Folks?
Eliminating it from both
Lambda?
the first and second, or just one of them?
I just want to get rid of the lambda here. What's the quickest operation? Can I do addition, subtraction, division, or multiplication?
Division.
Yes, division. Let's try division. 1 over 2. Let's do equation 1 divided by equation 2. If you do 1 over 2, then lambda will be eliminated right away, right?
Mm-hmm.
Leaving y over x equals 2. The lambda will be gone in no time. And 2 and 2 could be reduced. And I have basically x over 9 over y over 16, right? So that is y over x equals to, let me see, let me put the 16 on top. So 16x over 9y. Is this okay?
Mm-hmm.
That tell us, let me do cross multiplying. That tell us 9y squared equals to 16x squared. Right?
Mm-hmm.
Okay. Which I can solve for y squared or solve for x squared. Suppose I'm solving for y squared. I'm getting y squared equals to 16 over 9 x squared. Let's call this equation 4, because there's already equation 3 labeled. Good so far?
Mm-hmm.
So we can see that by using equation 1 and 2, we've got rid of the lambda. In addition, we've known the relationship between y squared and x squared. So now let's go ahead and use the equation 3 we haven't used so far, right? So plug this equation 4 into equation 3. Let's put this 4 into equation 3. I can forget about this negative sign, because the negative sign won't, I can just multiply negative sign both sides. It won't change the equation. So I have x squared over 9 plus y squared over 16. So y squared, so 16 over 9 over 16 minus 1 equals 0, right? Are you guys following me?
Mm-hmm.
Okay, let's see. So 16 and 16 could be reduced. We have 1/9 x squared plus 1/9 x squared. So that's 2/9 x squared, right? 2/9 x squared would be 1. If I move the right 1 to the right hand side. Telling you x squared would be 9 over 2. Is that good?
Mm-hmm.
Okay, so x squared equals 9 over 2. Then we can calculate the x value, right? So x would be plus minus root of 9 over 2, which is plus minus 3 over root of 2. Correct?
Mm-hmm.
If the x has to be in the first quadrant as we originally defined, okay, x is in first quadrant, then we pick the positive sign. So let x be the positive 3 over root of 2 in first quadrant. So we've got the x value, right? X value. How about the y value?
Plug x back in.
Plug x back in the relation between x and y. Remember, y squared equals 16 over 9 x squared, right? So here, y squared would be 16 over 9 times x squared. X squared is 9 over 2. So 9 over 2. So 9 and 9 would be reduced. 16 over 2 would be 8. So y squared would be 8, which means y would be root of 8, which is 2 root of 2 in the first quadrant. So this gives us the point in the first quadrant. Okay, in the first quadrant, that will give you the maximized area. X will be 3 over root of 2, and y would be 2 root of 2. Is that good?
Would you have to do the same thing to find the other 3 points?
The other 3 points? Theoretically, you don't have to do it because, let's see. Let me bring up the graph over here. So we found this point, right?
Yeah.
In this question, we have specifically defined x and y to be positive. If you eliminate that constraint, x, y being in the first quadrant, then you can find the other 3 points by using the symmetry. Currently, we said x is it 3 over root of 2? And 2 root of 2, right? This is the point. And it's easy for you to find the other 3 points. For example, this point in the fourth quadrant would be 3 over root of 2, x is positive, y will be negative, right? Negative 2 root of 2. This point right here would be both negative, negative 3 over root of 2 and negative 2 root of 2. And this point here would be x is negative and y would be positive, right? But if you're only looking at this critical point, I mean, this important point, then you just say 3 over root of 2, 2 root of 2 would give you the maximized area of the rectangle.
Okay.
Yeah. Let me just quickly review what we just did over here, okay? So we first of all write down the constraint optimization problem based on the question, maximize the function subject to this constraint. And then we figure out what is our constraint function g of xy. You gotta make sure the right-hand side is 0 for g of xy. So here you just need to move the 1 to the left-hand side. And then you form the function by using the objective and constraint. So it's f of xy minus lambda times the constraint. So that comes down to here. Then you take 3 partial derivatives and set them equal to 0. The rest of the work is all around solving the system. Once you solve the system, you get x and y, and those will give you the maximized area. Okay. I've attached my solution to the here. Okay, so you have the maximized area. If you calculate it, it's going to be 24. Okay, 24. All right, I think it's about the time for us to finish today. Sorry, I'm a little bit over for a few minutes. But any questions, folks?
No.
Okay. What about Donovan? Donovan?
I have a question.
Yes, you usually have some questions. The rest of you guys, if you want to leave, you may go ahead and leave. Okay. Yes, Donovan?
Plugging in, what is it, x back into one of the functions, we use function 4.
Let me see. I won't let me go back. Okay. Which one? Here?
Yeah. Would it be the same thing just to plug it into function 3?
Function 4 or function 3? Sure, absolutely. You can do both. Yeah, as long as the
algebra to solve it.
as long as the equation comes from the system, you can use any of those.
Okay.
So you can plug back in here. You can plug back in there. Okay.
Okay.
That's fine. All right. So let's meet next time, guys. And then I'll also follow up with the take-home test. Okay. So I'll go ahead and make the take-home test, and once it's ready, I'll upload it onto my courses and send you guys an email. All right, thank you.
Thank you. Bye.
Bye bye.